Hey guys, so we are going to solve Leecode number 133, copy list with random pointer. This is my first time seeing the problem, and I'll be here solving the problem with you guys. So first, let's read the problem statement. So we are giving a linked list such that each node contains an additional random pointer which could point to any node in the list or null. Okay, so we are supposed to be returning a deep copy of the list. So here's an example. We have a node 1 pointing to node 2, and then next pointer, and then this random pointer is pointing to node 2, which is pointing to itself. So we are given some sort of a dictionary that has been stringified, and within this dictionary object there's the ID key that contains a string of 1 and then ID of, and then also a key next that points to another object next. That essentially each object is a node, and this next key is pointing to the next node. Okay. Let's see. So let's first write down a number of questions that we can use to help clarify this problem statement. And if we ask the right number of questions and the right kind of questions, we should be able to derive the solution correctly. So the first question that I have is, which we'll go over quickly, is what is a deep copy? Okay, so from reading this quickly, I believe deep copy is exact copy of either a data structure or a linked list. We are meaning we're not just copying the reference to an object. We are making a real duplicate that resides in another memory location. So we're not just copying a reference. We're making a real copy. So for this case, we are making deep copy of a linked list. So which just means that it's going to be a new list with the exact same data. Okay, so let's ask our next question. So okay, so let's ask some other questions. So let's say, so for this question, let's ask ourselves, what is the brute force solution? What is the optimal solution? Identify bottleneck. Okay, and let's see. So let's quickly go over our input parameters. Input, output. Okay, so for our input, we are given a reference to head pointer, reference to head of the list, and output is copy of the list. Copy of the list, right? Okay, so let's think about a solution to this problem, right? if this list were to be a straightforward linked list where we only have a head node, and that head node points to the next node, and that node points to the next node until the end of a list, we can simply traverse from the head node to the end of the linked list, and at each iteration we simply have to make a new node that has the same data as that node, and we can pretty quickly iteratively create a clone that way for a straightforward linked list. However, with this list we have an additional random pointer that points to any random node, right? So let's write down some of our approaches. So let's think this through, right? Sorry about that. So simple linked list. So for a simple linked list, we can, traverse from head to tail, making copy of each node along the way. So we can do this in of n time, right? So now let's ask ourselves, for this list with random reference, so let's think about this. So why can't we simply do the same approach, or can we? Maybe we can. Let's see. So what is an obstacle? What is giving us a hard time? Why can't we simply traverse the list from left to right? Let's think about it. So okay, so how can we overcome this this problem? Because we have a random reference that points to any random node, we do not know whether that node has already been created. As we traverse from left to right, from head to tail, we don't know if this random reference points to a node that we had already cloned. So in order to overcome that, in order for us to not create a duplicate of that node, let's say we already created that node, we can keep track of current node and new node, right? Let's say this random pointer points to some random node that we have already created. In order to set this random reference to the correct new node, we simply have to look it up in some sort of hash table where the values are reference to new node, key reference to old or current node. Right, so let's write this down quickly. So in order to overcome duplication, so in order for us to overcome creating duplicate nodes that we have already created, when setting reference for random pointer, okay, so we can keep track of current node and a new node in hash table. Values are reference to the new node, key or reference to the old or current node. Okay, in original list. Okay, so now let's see. So what happens if that node hasn't been created? what happens when let's say this random reference is at the beginning of a list and is pointing to the end, right? So what happens? So in that case, we can create the reference new node on the fly and store that in our hash table. And so when the time comes for that, that node towards the end of the list to point to this next node, which we have already seen earlier within the list, we can simply look it up in our hash table if this node has already been visited or created, right? So so all we have to do is look up. Essentially, as we iterate through the list and create a new copy, check if already created in table, right? That's all we have to do. Okay, so with this solution, if we were to do this solution, let's see, overcome creation of so let me rewrite this. Overcome creating a new node that's already created when. So with this solution, it'll take us O(n) time and O(n) space because we have to keep track of this lookup table. So now let's quickly think about what is the optimal solution. So can we do this with O(n) space of one space? Can we do this in such a way that we don't need a lookup table? Okay, I'm not going to answer that now because I can't think of anything at the moment. Okay, so let's leave this question open-ended. So as we code the solution, we'll revisit it. Okay, so now let us implement our initial solution, which is keeping track of a lookup table as we iterate through the list and creating a new node. Okay, so for this we'll need so let's create our lookup table. So what we said earlier is that key is node of original list value key is node. So let's call this let's see, is reference to new list. Okay, so key is actually we'll use address. So key will be address of node in original list. Value is reference to node in a new list. Okay, so now we simply have to iterate through this. So let's set our new head to none, to nothing for now. Let's see, and what else? And what else do we need? Okay, and we also need a pointer that will point to head. And now all that we have to do is we can traverse to from head to tail. So while pointer is not equals to none, the first thing that we'll do is we check to see if this exists within our lookup table. Actually, the first thing that we have to do is, if new head goes to none, we'll have to create our head pointer, which is okay, what am I doing here? Okay, so you know what, let me try this again. Let's see. So if id in lookup, let's see, what are we doing here? Let's think about this. So we need this new node sets to none. Okay, so if it's in the lookup table, then we'll simply do something like this. It goes to lookup. So all we have to do is look up this table if it's already exists, retrieve the value. If it doesn't exist, then we'll create a new node. Let's see, so new node equals to node, and we'll do pointer dot value, pointer dot next, pointer dot. Okay, so we cannot update random just yet because random hasn't been, we don't know if random node, where the random node is, so we still have to look that up. Okay, so let's do that for now, and let's see, and we'll also update our lookup table with the new, let's see, right, so we'll also update our lookup table with the reference to the new node, where the key is an address of the original node. Okay. Okay, so now that we have the new node, all that we have to do now is first thing that we have to do is check if new head is none. If it is, then new head equals to new node, else new head dot next equals to let's see. Okay, so we need to also keep track of previous new node. Okay, new previous equals to none. Okay, so we'll use this pointer to keep track of our current node within the new list. Okay, so new previous equals to dot next equals to our new node here, and new previous equals to new node, right? Okay, so now, as you might have already seen, we still haven't updated our random pointer. Okay, so now we can do the same thing up here, where we look up whether this new node already exists within the lookup table. So we do the same for random. Okay, so now all that we have to do is we do something like this. If id pointer dot random in lookup let's see, we should do that up here. Now that I think about it, it's better to do it up here before we move on forward here. So now we'll look up our random pointer. Okay, let's see. So a new random, let's set that to none for now. So if it is within our lookup table, then we'll simply do lookup id ptr.random, else we'll create the node on the spot. So we'll do something like this: new random equals to node. Okay. So here we run into a problem that I hadn't thought of as we were solving this problem, is that what happens, so as we update this new random pointer, we don't know whether the random pointer, the random reference within this random point within this random node is not going to indefinitely point to some other nodes. Okay, so it does seem that we need to define a new helper function that we would call update random, which will essentially recursively update our random pointer until, let's see, when does that end, right? So what I'm trying to say here is that we need to recursively update our random pointer until all of the necessary nodes are created for the random references. Let's see, let me think about this a little more. Okay, so let's see. So we need to update our random recursively. And how do we do that, right? So that's the question. How do we update our random pointer? Because we don't know where it's going to point within our list. We don't know if it already exists within our list. Okay. So let's see. Let me think about this. Okay, so what I'm thinking of doing is we'll recursively update our random references and keep creating the new node for the random and keep creating a new node that the random reference points to until all of them exist within our table. Okay, so let's try to write this out. So we'll pass in our lookup table, and we'll also be passing in our random node that we want to update. Okay, and all that we have to do here is we have to, so this is what this thing is going to return. Is it's going to return our new random node. So right now let's set it to none. So we'll return this at the end. Okay, so now all that we have to do here is we check to see if this random reference has already been duplicated, and we do that by checking to see if the address of this old original random reference already exists within our lookup table. If it does exist, then we retrieve the new reference to the new duplicated random to the new duplicated node that we have created previously. Okay, so that's what that is. If it doesn't exist within our lookup table, this is where we'll be calling update random recursively, right? So here we'll do self.update random. What we'll want to pass in is a random node of this a random reference of this random node, right? And so this recursion call will return a new duplicated random node for this random node. I know it's a little confusing, but bear with me here, right? So let's do that. So lookup. Let's see. Okay, so what we want to do here is we want to update all of the random nodes that we haven't created yet. Okay, so now that we get this new duplicated random node, we want to, the next thing that we want to do is we want to put this in our lookup table. So we can do, so what we could do here is this. So random equals to okay, actually the first thing that we have to do is create a new node. So new random equals to node random dot value random dot next. Another thing that we haven't thought of is we also need to update our next. Okay, so this problem so it does seem that we have made this problem too complicated. Okay, so let's solve this with a different approach. So instead of trying to update everything in the first go, what we could do is we can first iterate through the list from left to right, from head to tail, update our lookup table with the new reference, where the keys are the old reference. And once we have created our new list with updated next, we'll then go back and update our random reference of each node within the new list, and we'll do that by traverse from left to right in our new list and look up our random reference within our lookup table. So that way our solution becomes much simpler. So let's scratch this approach. And so let's try this again. So the first thing that we'll do, so let's write this down, right? So first create iterate from iterate from head to tail within original list, update store reference to new node in lookup table. So after that, so our first iteration will store references to the new node in our lookup table, as well as update next. So once we have a simple list created, okay, another thing that we have to keep, that we also have to do is set all random to original reference. So we'll keep all of the original references within our new list, and within our second iteration, iterate in from head to tail in new list, and for our second iteration we'll use the old original references of all of our random pointers that are stored within each of the nodes of our new list, and we use that to look up a new reference within our lookup table. Update all random references from lookup table, right? So this way our solution becomes much simpler. So let's try this again, and first thing that we'll do is while ptr is not equal to none, right? If new head not equal to none. Okay, so the first thing that we have to do is if new head equals to none, then we'll do ptr dot while ptr dot next. Okay, so we cannot update next yet. So we also have to keep track of new pref next, which we'll use to update let's see, what do we want to do here? Okay, we don't need to do this. Okay, so right. Okay, so let's keep going with this. So we'll set this to none for now. So we set our next to none for now, and we'll also keep the old random reference here. Okay, and we also have to point our new previous to the new node. Okay, else if head already exists and we are somewhere within the new list, the first thing that we have to do right away is create a new node, and we'll do pointer.val pointer, set that to none for now, and pointer.random, and our previous node next will point to this new node, right? And now our new previous becomes this new node. Okay, so we keep doing this until the end, right? Let's see, so we can reduce duplicate code by moving this new node creation out here, right? And then we'll put this here, and that should be it, right? So now the next important part that we haven't done yet is updating our lookup table, right? So now all that we have to do here is we can do something like this. We'll do id of pointer equals to new node. So now as we iterate to our linked list, original linked list, we are creating duplicates of each node while at the same time associating old pointer to the new pointer in our lookup table. So now, as I was saying before, within our second iteration we'll be updating our random references within our new list. So let's do that now. So while pointer is not equal to none, right? What we'll do here is okay, so let's do that first. So what we'll do here is we'll do random equals to pointer, so we do a lookup get. If it doesn't exist, we'll set it to none. Okay, so what we're doing here is we are updating our random references with the new nodes that we have created prior within this loop. And at the end of all this, we simply have to return our new head. Okay, so let's see if this code runs. Okay, seems to pass the initial test cases. So is that right? Yep. So before submitting this code, we should think about edge cases. Are there any edge cases that we haven't thought of? Let's see. So one thing that comes to mind right away is none. If the head is none, then we'll simply return none. Let's see. Anything else? Okay, I can't think of anything else. So let's submit this code and see what happens. Success. Okay, seems like it's faster than 7.47% of Python submission. So clearly we could do better, but we'll do that another time. Thanks for listening.